Uh, Once again we are coming back with one more presentation or the demonstration of how to generate a sine wave or a sinusoidal waveform using your digital to analog converter. So now when we speak about the sinusoidal waveform, we know that the sinusoidal waveform will be symmetric about the x-axis, right? But in a microcontroller we will not be able to generate like this because we don't have anything called the negative range of the voltage in the microcontroller. So whatever the sinusoidal waveform we are going to have, it would look something like this rather than what you can see in the first diagram. It will be something like this. So let us say that if this is the maximum value 5 volts, this will be 2.5 volts and this will be 0 volts, and in this way you should be able to generate the sinusoidal waveform. So now when I want to generate the sinusoidal waveform, your output of the digital to analog converter should follow this particular pattern. That means when you take this axis as a function of theta, so this as the output voltage V0. So now I should relate these two by means of a sine function. This is a very important point to be noted. So now what I mean to say here is, when theta is equals to 0 at this point, your output should be equal to 2.5 volts. Let us say that at this point when theta is equals to 90 degree, your output should be 5 volts. Then when theta is equals to say 180 degree, the output should be same as that of theta equals to 0, that is 2.5. So when theta is equals to say 270 degree, your output voltage should be 0. So this pattern has to be followed, but you should also keep in mind the in between values which should follow a sine function. So this particular thing can be achieved by having this particular formula: V is equals to V by 2 plus V by 2 into sine theta. So now in this particular formula, if you substitute the value of theta right from 0 to 360 degrees, whatever may be the intervals that you have here. So if you have large number of intervals, you will have a smoother sine wave. If you have less number of intervals, you will have intermittent sine wave. So now if you substitute theta is equals to 0 here, definitely you would get, if your V is equals to 5 volt, maximum voltage is 5 volt. So in this case, when theta is equals to 0, this part will become 0. You will have V0 is equals to 2.5. Similarly, when theta is equals to 90 degree, this becomes 1. 2.5 plus 2.5, you will get 5 volts. When theta is equals to 180 degree, again you will get 2.5 volts. When theta is equals to 270 degree, this will become minus 2.5 plus 2.5, you will get 0. So this is the formula which is required to be used here to generate the sinusoidal waveform. So now when I say that I have to vary the value of theta between 0 to 360 degrees, so let us say that I have got x intervals, right? So this x can be 10, or this can be 20, this can be 50, or even it can be 360. So all these values of x, that is the value of theta, should be put in what we call it as a lookup table. So these values are to be called every time, and accordingly, depending upon the value of the theta, the values will be designated to the output voltage, and you are going to get the waveform like this. So now for that we will have to write the program. Once we write the program, once if you burn the program into your microcontroller and connect it to DAC from the designated ports, you should be able to have the display of the sinusoidal waveform with whatever the accuracy you have, depending upon how many number of intervals you consider between 0 to 360 degree. So this is the basic information about the generation of the sine wave. Now let us go into the programming part of it. So needless to mention that the basic things we are already aware. So here let us look into the program. So the header file has been included here. Now please see here, x data unsigned character sign underscore tab 49. So I am using a lookup table here. Please look here. This is my lookup table, and this lookup table has got 49 values. As I have already told you previously, it is the value of X. So now let me start from 80. The first value is 80 because I will have to start from a voltage of 2.5 volts. So this 2.5 volts must correspond to 80 because 0, 0 to FF should correspond between the voltages 0 to 5 volts. So my first value here in your lookup table will be 80. Now depending upon the total required values. So when I start from 80, suppose if I start from 2.5 volts here, I will go in this direction, I will reach 5 volts, again I will come back to 2.5, again I will go to 0, then again I will bring it back to 2.5. This will complete one cycle. So from this point onwards, the cycle repeats. That means if I start from 80H, again I have to stop at 80H only. So the in between values are to be properly taken care of depending upon how many intervals you are having between 0 to 360 degrees. So that's what is shown here. I start from 80, then the next value is 90, then A1, B1, so on and so forth. So I will reach a maximum value. Say, let us say that maximum value you can see here, E5, right? This is FF here, the maximum value is FF. So now on either side of FF you have FE. You can see here FE is here, FE is here also, right? On either side of these FEs you will be having FB here, FB here, because you will have to have a symmetric waveform. So after FB you will have F6 here. So before FB you will be having F6 here. So in this way from 80, okay, you will go up to FF, then again you will come back to 80. In the same manner you will proceed for the next half cycle. So you will again reach up to 80. So you started from 80, then again you will come back to 80. That again I will demonstrate with the help of this diagram. So you start from 2.5, again 2.5, this is also 80, then you will go in the reverse direction till you reach 80. It is something like this. One more diagram I will draw. So this is 80, this is FF. So on either side of FF you will be having the different similar values, then you will go up to 80 here. So this is one cycle which I should call it as the positive half cycle, though it is on the positive side of your x-axis only. But from 80 onwards again you will go up to this point, right? So which corresponds to the minimum value till you reach 80H. So all these values are stored in the lookup table. Once if you write this lookup table, once if you draw this lookup table, your most of the task is over. Now see here, suppose if I want to have 360 intervals, will it be possible for you to remember these things? It is not at all possible. That is the reason why I told you not to by heart these things, but these things can be calculated, right? Anyway, after this we will share you the formula to calculate these things, and accordingly you can decide what will be the first value, what will be the intermediate values, and what is the last value for 49 values. The same thing holds good for n number of values from 0 to 360 degree. That particular formula will be shared to you afterwards. Okay, so now once this value is stored in the lookup table, these 49 values are stored in the lookup table. The next task is very simple here. So idata integer count. Now this loop will be executed indefinitely, while one loop for count equals to 0, count less than 49 as per the requirement of your numbers in the lookup table. You will have to simply increment the counter. Now once the counter value is incremented, you know how to output these values. Now deliberately we have used two ports here. In the previous example when we discussed about the triangular waveform, we had used only one port. Now let us try to see how you can realize the functioning of the dual DAC. So both P0 as well as P1 are designated as the output ports. So therefore in the dual DAC, both the DAC outputs should be you should be able to see on the CRO. So now once this particular program is understood, the next part is very simple because it is similar to what we did in our previous case. So here we have already created the hex file of this particular program. This particular window I have opened only to make you understand about the program. Okay, so now we will go to the next part of it, that is the flip. So I will go to the flip here, very similar to what we did earlier. Okay, whatever is not reset, that we will reset here. Then again the settings, communication, RS-232 with the default values, connect, start application, all these things will be fine. Then I will go to the file, load hex file. So in this we will have to again go back to our desktop here where I have stored my EEE file, MCEE file. So here this is in sign. So this sign hex is now getting opened. I hope you have followed this. This is very simple. So first time it may appear to be a little difficult, but once you get familiar to these things, this becomes very simple. Okay, so now you can see here the sign hex file has already been included, 2.2 kilobytes. Now the next task is to run this particular program. As we are already aware, it will take a few moments here before the previous program is erased, blank checking is done, programming is done, and till it is verified. Okay, so now you can see the screen there. We have not yet got the output because I have not pressed the start application here. Now I am pressing start application, and you should be able to get the sinusoidal waveform on both the channels because I have used P0 as well as P1. So the dual DAC here, if you look at the dual DAC here, there are 4 wires. The 2 middle wires are the ground points, they are same. So on the extremes you will have the outputs of the DAC 1 and DAC 2. So this pink wire is corresponding to DAC 1. This black wire is corresponding to DAC 2. So similarly, those wires have gone to their respective terminals on your BNC. So this and this are common. You can see here, these two are common. You can see here, this point, right? So this wire and this wire, they are common. And black is one of the outputs of the DAC, one DAC. And this pink is the output of another DAC. And accordingly, you will see both the outputs. So this is how you demonstrate the sinusoidal waveform generation using the DAC. Now, we shall also use the logic analyzer, right, in order to demonstrate the waveform as we did it in the case of the triangular waveform generator. So now I will reset it, and you can see there the waveform gets blank, right? Once I reset it, I have nothing to do with the DAC now, but what I have to do is with respect to this program. So here I have already told you that whenever we want to use the logic analyzer, one thing you should note is that here in the debug, instead of using Keel Monitor 51 driver, I must make use of the simulator. So this has to be unclicked and this has to be clicked. That is the only change, right? So now the same program I am using here. Now let me go to the debugging part of it. I will start debugging. So okay, now once it is debugged, now I am going to the peripheral IO ports, port 0, and even I can show you the port 1 also because I have got both the ports in my program. Then I will go to the logic analyzer here, right? So I will just bring it down here, both ports. Once I go to the logic analyzer, I will click on the setup. So anyway, both are clicked here. I will once again do it. So you can see here P0 is designated now, okay, with this blue color. Then I will designate P1 as well. So that will definitely take some other color. Let me take it red here. So close. Okay. Now we have not yet started. So you can see here it has already reached the maximum value. This is the default value from where it should begin. Now once I run the program, I should be able to get the sinusoidal waveform. You can see here, I will zoom it, right? And you can also see You can see here the resolution is not that good because between 0 to 360 values we have used only 49 steps. That is the reason why the resolution is not good. You can make use of all the intervals and accordingly you should be able to get a smoother waveform here also, right? So this is how you should be able to obtain the waveforms on the logic analyzer as well. You can see here, right? You can see the waveform. So this will take us to some different things. Okay, now you can see here I can change the frequency also, adjustment also, similar to what we do it with the help of the time per division knob in the CRO. I hope you have followed these things and you can try these things on your own. Don't say that we don't have the CRO with us. So this itself is the virtual CRO for you. Please try these programs and try to understand by creating more points rather than only 49 points as we did this in this program. You take 72 points, you take more number of points and observe that your sinusoidal waveform becomes smoother, right? So with that we are stopping this presentation. Again we will come back with one more presentation on the ramp waveform.
Please refer this formula to convert formula into hexadecimal equivalent value for sinusoidal array or lookup table.